Hi, it's Mrs. V here, and as I record, it is May the 4th. So, happy Star Wars Day to all. May the 4th be with you. Today, we are going to be talking about an introduction to covalent bonding, and we will be looking at electronegativity and Lewis dot structures. So let's get the whiteboard on and get started. In previous videos, we've talked about metallic bonding and ionic bonding, and it's been quite easy to talk about the fact that when you have an ionic bond, metals want to lose electrons, non-metals want to gain them, and so it's a pretty easy situation where the metal can give its electrons away and the non-metal can gain them, and everybody is happy. But what about when two non-metals bond? Now, we actually know this happens. We know that a compound forms between nitrogen and chlorine. We know that happens. So we need to come up with some bonding model that explains how two non-metals that have high electronegativity, and we are going to spend a bit of time talking about electronegativity today. So two non-metals have high electronegativity. They both want to gain electrons and they both want to complete their octet, but somehow they are able to bond. Okay, and we know this because we know that compound between nitrogen and chlorine, which is called nitrogen trichloride. We know that that forms. So let's explore some of the concepts involved in this. We won't get to the actual covalent bond idea this lesson. That will happen in our next video. But let's just talk about what we mean by the term electronegativity. So electronegativity is the tendency of an atom to attract bonding electrons. And we're going to talk right at the end of this video about what we mean by this term bonding electrons. But we're going to start talking about electronegativity. Now, atoms are assigned electronegativity values on what is called the Pauling scale. This is after Linus Pauling. So Linus Pauling lived in the 1900s. He won 2 Nobel Prizes. He won the Nobel Prize for Chemistry in 1954 and the Nobel Peace Prize in 1962. He was actually married to a great peace campaigner. Only 2 people in history have ever won the Nobel Prize in 2 separate categories, Linus, and the other one was Marie Curie, who won the 1903 Nobel Prize for Physics and the 1911 Nobel Prize for Chemistry. So that's a bit of background on Linus Pauling. So he is famous for, among other things, he's done quite a bit in the field of chemistry. He's known for his work on electron pairs and on electronegativity. So we can see the lowest electronegativity atom on the periodic table is cesium. So cesium has the absolute worst ability to attract bonding electrons. That's probably why it loses its electrons. The best is fluorine. Fluorine has the highest electronegativity at 4.0. These are relative values. They don't have units, so they're used to compare the elements, but it's not something where you can actually stick a probe into an atom and get a value for its electronegativity. And so these values are assigned, not measured. So it's the relative ability of an atom to attract what we call electron density. All right, let's have a look at how these values are assigned. So the periodic trends in electronegativity, we see that electronegativity increases as we go down a group on the periodic table, and it increases as we go across the periodic table. Oh, sorry, electronegativity decreases down the group, not increases. So overall, we have from here to here, we have an increase in electronegativity. I'm going to call electronegativity EN because electronegativity is a long word to keep writing. So let's have a look at why, first of all, electronegativity decreases as you go down a group. So let's have a think about why there would be less attraction for the bonding electrons. Remember, they're in the valence shell as you go down a group. So let's have a look. Here's our nucleus of the atom in the middle, and we've got a bonding electron there. What affects the force of attraction between the nucleus and the valence electrons? First of all, size of charges. Remember Coulomb's law. And secondly, the distance between the charges. Now, the main difference as we go down a group is that every time you go down to the next atom, there's an extra electron shell. So the valence electrons are getting further and further away. So valence electrons further away. And this has a huge effect. And particularly, we have inner shells. Inner shells provide what's called a shielding effect. So having that big chunk of negative charge, so if we have our nucleus in the middle here and our valence electrons on the outside, then all of these electron shells in between here, it's a big chunk of negative charge and it shields the valence electron from the nucleus charge. So not only do we have a distance between the charges increasing, so this is, so that increases as you go down the group. But you also have the inner shells providing shielding. So overall, the attraction of the nucleus for the valence electrons is less. Remember, the valence electrons would be the bonding electrons. So as you go down the group, your electronegativity is going to decrease because you simply don't have as much attraction between those bonding electrons and the nucleus. Let's have a look as we go across a period now. As we go across a period, the electronegativity increases, so we have a stronger attraction. So as you go left to right across the period, you get a stronger attraction. What could be causing that? Within the same period, the distance between the nucleus and the valence electrons, there's always the same number of shells. So distance is the same. Distance turns out to be slightly decreased, but the same number of shells means that you've got the same shielding. And your distance is about the same. The atom actually gets a little bit smaller, and we'll talk about that in just a sec. So what's causing the increased electronegativity? Well, every time you go across by one element, you get an extra proton and an extra electron. So the charges are higher. So it's higher charges. And if you remember Coulomb's law, the higher the charges, the stronger the attraction between them. And in actual fact, this stronger attraction causes a bit of a shrinkage as you go across. And we say, the way we talk about the size of an atom is this term atomic radius. And so the atoms shrink as you go across. And that actually enhances the attraction of the nucleus for the valence electrons or the bonding electrons, because not only are we looking at higher charges, but we're getting the atom itself is getting a little bit smaller, which means that the valence electrons are just that little bit closer to the nucleus. So overall, that causes an increased force of attraction, and that's why your electronegativity is greater. All right, so that's what we need to know about electronegativity for our study of covalent bonding. Let's talk about what these bonding electrons are. We keep talking about bonding electrons. We're going to study what bonding electrons are using Lewis dot diagrams. These were developed by Gilbert Lewis. He lived from 1875 to 1946. He discovered covalent bonds. Pretty amazing discovery. You'd expect him to be certainly winning some Nobel Prizes, but he was in fact nominated 41 times to win the Nobel Prize, and he didn't get a single one. He has an interesting story, actually. He was very prominent chemist, studied at Berkeley University, and he was studying thermodynamics with Nernst. And if you study thermodynamics, you'll study the Nernst equation. And he actually said that Nernst's work wasn't that good. So he really annoyed Nernst. And unfortunately, Nernst had some buddies who were on the Nobel Chemistry Committee. And it is suggested, very controversially, that because he'd criticised Nernst's work, Nernst's friends on this committee always blocked his winning of a Nobel Prize. So very sad for Lewis. He was actually found dead in his laboratory in 1946, and he'd actually been working with hydrogen cyanide in his lab, so he died of cyanide poisoning. And there was certainly an inquiry as to whether he'd actually suicided, which is a very sad story. But let's remember Gilbert Lewis for his great work in chemistry. Even though he didn't win a Nobel Prize, both of his sons went on to become professors at Berkeley University, and he has a hall at Berkeley University named after him. So he certainly is remembered for his great work. So these Lewis dot diagrams, they're also called electron dot diagrams. I wonder if that is Nernst trying to remove our memory of Lewis. So, also called electron dot diagrams. But I'm going to call them Lewis diagrams because I'm going to remember Gilbert Lewis and his great work in chemistry. So electron dot diagrams, they just show the valence electrons as dots. Sometimes you can use crosses if you're looking at different, when we start drawing Lewis diagrams for molecules, we will want to be looking at the electrons that came from different atoms. We might use dots and crosses. Usually I always use dots in just different colors. So looking at the elements number 1 to 20 on the periodic table, let's have a look at the Lewis diagram. You'll notice all of the elements that are in period 1, sorry, not period 1, group 1, all have one valence electron. And so they all have just that valence electron shown as this little dot. In group 2, we have 2 and so on and so forth, but there is a particular way you've got to set this up. If we choose, let's choose phosphorus as an example. Phosphorus doesn't get enough popularity in examples. Let's look at phosphorus. So phosphorus is in group 5. And therefore it's got 5 valence electrons. So when we draw the Lewis diagram, we draw the symbol for phosphorus, P, and we go, it doesn't matter where you start, and it doesn't matter if you go clockwise or anti-clockwise. I generally start at the top and work clockwise, but that's just me. So to put those 5 electrons on, we go 1 on top, 1 to the side, 1 down the bottom, and 1 to the other side. Now, once you've done that, you can start doubling up. So the 5th electron doubles up. When you've got the Lewis diagram shown, some of the electrons will be in pairs, and they're called non-bonding electrons. Whereas others, the ones that are not paired up, are called the bonding electrons. Let's try one more example. Let's have a look at fluorine. So fluorine, draw the F, it's in group 7. So it's got 7 valence electrons. So again, we're going to start at the top, 1 to the side, 2, 3, 4, 5, 6, 7. You can see that fluorine has 3 pairs, 3 non-bonding pairs. And it has 1 bonding electron. I'm sure it's not much of a stretch for you to realise that what this means is that phosphorus can form 3 bonds and fluorine can form 1 bond. So the number of bonding electrons tells you how many bonds that atom can form. That's enough for this time. I will see you in the next video when we look at Lewis diagrams. Remember Gilbert Lewis, and we will be doing Lewis diagrams for molecules. I will see you in the next video.